Alright, so today I want to talk about finding the acceleration of this system right here. And we're going to note that we're just going to observe from the masses that we're going to find the acceleration to go in this direction. So it's going to be accelerating downward. This is going to be accelerating this way. And this cord has no friction. So that means the tension is uniform. So first, we got to find the forces acting on this box. So we're going to do this in blue. So this box, what we determine with this will be in blue. So let's do that down here. We're going to have this box. Call it M. This angle theta. And we have a force pulling it up. We'll call it T for tension. We have a friction force backwards. And that is slowing down the acceleration of the system. We also must note we have a normal, right? This normal is stopping the box from falling through this road or whatever it's on. We must have a gravitational force acting downwards. So let's draw this downwards, and we'll draw this to be the weight. And weight is the force of gravity, and that's going to equal m times g. So let us also define our direction. So we're going to call I hat, or the x direction, to be positive that way, and j hat to be positive up. So what is our normal force, right? That's something that is important to find out. Well, we need to find out this component coming out, which must be equal to some vector this way. I don't know if you can see that, but if we draw this, right, the weight vector, we're going to have a component this way of it, right? That means we're going to also have a component this way, which is what's pulling, which it's slowing down the movement of the system. See, if there's going to be some angle here. We don't know what the angle is, but we can find it through some trig. So we know that this, draw here, this is completely orthogonal or perpendicular to this plane. And we know what else? Well, we know that this, right, and this angle here must sum to 90 degrees. And we'll call this angle alpha, right? So that means alpha plus this angle must equal 90. Also, see, if we take this and we draw this line here, well, what do we see? We see this triangle here, which means alpha plus alpha plus theta must equal 90, but also alpha plus this angle must equal 90. So we see that alpha equals this angle on the inside. So that is really important because it's very useful to know that angle. So we're now going to draw, well, we see that if we take this angle, we take the cosine, right? The cosine. We're going to get the magnitude going into the plane here. So we're going to have the force in the j hat direction, sorry about that, it's going to be equal to, well, we know the acceleration is going to be 0 because it's not going anywhere here, it's not going anywhere there. 0, which is going to equal mg cosine theta, because we see this angle's right here, this is the hypotenuse, right? It's going to be cosine of theta times the weight, and that is equal to mg, as we said over here. Now, well, we know this can't equal 0, so we must have some other component that's equal to that. Well, that is the normal. And we see that when we solve for it, we get the normal force is equal to cosine of theta times mg. And that is our forces in our j hat direction. Now, let us do, we'll do it in a different color, a fun color. We'll do blue. I already did blue. Let us do, it's not really important, let's do gray. So now let's find the sum of our forces in our I hat direction, which we defined over here to be positive this way. And side note, I define it to be positive this way, but I make that negative. I should have made this positive and this negative, but it wouldn't have made a difference. So I'm sorry, I do apologize. I actually forgot I wrote that. So we're going to say that it has some mass times acceleration, and vectors have these hats on top in case you didn't see my other video. We're going to draw this hat because it has a direction, right? We know it's going to be this way regarding this mass. And that's going to equal this tension, right, which is pulling up, and it's in the positive I hat direction. We see it's going the same way, right? And then we're going to subtract the forces opposing it. We see that's a minus force of friction, right? And force of friction opposes anything that moves, right? So if you have an object here, and you pull it this way, you're going to experience a force of friction this way, and that's going to produce, heat. If you pull it this way, right, you're going to produce a force of friction the other way. So it doesn't really matter which way you move it, but you'll experience a force of friction either way. And then we're going to subtract, right? Well, we talked about this. We want this component, right? This weight, right? This force of down is having a force in the I hat direction equal to, well, this angle, theta, and that's sine of that angle. So we're going to do mg, right, which is the weight, sine of theta. So now, now we know our forces regarding this mass. Let us now do it regarding this mass. And I will highlight this in red, and we will do that mass over here. So we have this mass big M. And we know that the force of gravity, mg, is pulling it down, and we're going to do this big M and g. We also have a tension force up, right? And that's going to be T. So we're going to define our positive direction to be down, right? Just so, because that's where it's moving, it's easier. This will be the J hat. We'll make I hat this way. We see there's no forces acting this way. And I want to make something very clear. You can call any direction positive or negative, and it will work out the same algebraically. I encourage you to try this and see how the signs turn out. So we're going to see that in the J hat direction, do this in light blue, f of j, and I encourage you not to confuse this with this f of j. They are different, right? We define a new axis, right? It's different. And this is going to equal, well, let's think about it. mg is positive, and tension is pulling the other way, minus tension. And this will equal, well, that's a horrible g, I'm so sorry, the mass times acceleration. And this is big M. I apologize again. That's all the forces. We see there's no forces acting in the I hat direction. So we see that mass times acceleration equals mg minus tension, right? So how can we add these, right? We have f of j. How can we add these to get something out of it, right? Let me zoom out a bit. Well, this is the j hat direction, and this is in the I hat direction. This is in the j hat direction. There's nothing we can do with this. We see that's n equals. There's not much we can do. Well, we have to use our physical intuition here, right? We need to apply some physics and deep thought. We know that the acceleration of this entire system is uniform. So that means this A right here must equal this A, right? So what we can do is, even though these are different directions, we know this whole system, this acceleration, must equal this whole systems. So let us do this, and let's do this in orange. Right? So we're going to do MA equals mg minus t plus little m equals tension minus the force of friction minus mg sine of theta. We're going to do m times a plus ma equals, well, this is going to go away. Okay, mg minus the force of friction minus mg sine of theta. Now we could have also over here solved for t and then plugged it in, and that would have been easier, but I did choose to do it this way so you could see how it also works. So we can factor out an a. We're going to get m plus m equals mg minus mg sine of theta. Now, what is the force of friction? We talked about that earlier. We're going to get that the force of friction is equal to u, well, it's moving, kinetic, times the normal. And we solve for the normal over here. So we're going to get uk, this is a vector, uk cosine of theta times mg equals the force of friction. Now we can substitute that in over here. So we're going to get uk mg cosine of theta. Now we can just divide here. Just take that, divide it over here. We're going to get acceleration is equal to mg minus mg sine of theta minus uk mg cosine of theta divided by m plus m. So we also could factor out, we can factor out a g here, right? But let's just leave it. Now let's see this equation if it works. So a good way to test that, in my opinion, is to take this mass and set it equal to 0. So we're going to take a limit, right? So we're physicists. We like limits. The limit as this m, which is small m, approaches 0. And this is of this acceleration function. So we're going to say, we're going to get mg, well, mass is 0, this whole thing goes to 0. This whole thing is going to get a minus 0 minus 0. You're timesing this by 0, and the number times 0 is 0. And then we're going to get m plus m. So we get m plus 0, which is equal to mg over m. The m's cancel out. You get g. Well, let's see if that makes sense, right? We have, well, this goes to 0. It's just going to free fall. And it's going to free fall at what? Well, it's going to free fall at gravity, speed of gravity. So it does work, and this equation is correct. You can give us a little check mark, a little happy dance. I really thank you guys for watching my videos, and please let me know if there's any other videos I can make for you guys. Oof, I'm so tired.